All right, everybody, thanks for attending this seminar. We're going to get started in just a minute. Just want to let you know we got basically 60 seconds to smoke them if you got them. So we'll be back in just a minute and get started. All right, good afternoon, and thank you for joining us on our call today. My name is Mike Crittenden from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Battery Testing 101. The topic is being presented by Andy Sagl from Megger. Andy is the product manager for power quality and battery testing. He's worked with Megger for 14 years, and he's a specialist in power quality and battery testing technology and applications. He develops and supports power quality equipment in addition to writing power quality and battery publications. He also teaches training and seminars courses. His degree is in electronics, and he's a member of the IEEE Power Engineering Society and Battery Standards Group. We expect today's presentation to last roughly 30 to 40 minutes, and then we'll answer any questions that have been submitted. Anytime during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Andy.
Hello, everyone, and welcome to Battery Technology and Maintenance 101. And our agenda for today is we're going to cover quite a bit of items here. We're going to cover types of lead-acid batteries, the battery applications, battery failure modes, battery maintenance, particularly maintaining VRLA batteries and maintaining VLA batteries, vented lead acid, and also the issues that we see in testing parallel strings. Let's start off the battery types. Okay, we're going to start off with the basics. You have the primary cells and secondary cells. Primary cells, these are the cells we're all familiar with. These are our Duracell or Energizer, and when they die, we throw them out. They're called primary cells because as soon as they're manufactured, they are fully charged. Secondary cells, these are our rechargeable batteries. These include lead acid, NiCad, lithium ion, and they're called secondary cells because when they're manufactured, they don't have a charge. They have to have a secondary operation to charge them up. We're going to be dealing with the secondary batteries here. And we can further break them down as cyclic batteries and standby batteries. Now, cyclic batteries, these are the ones that are used on a regular basis. They're charged and discharged, commonly used in automotive applications, golf carts, forklifts, things like that. Then we also have standby batteries. These are the batteries that remain charged, and they stay on charge unless they're absolutely needed. These are what we're seeing in substations, telecommunications, data centers, wherever we have backup applications. And of these batteries, we can look at, we have both lead acid, vented lead acid, VLA, and we also have valve-regulated lead acid, VRLA. They're quite different. The flooded VLA batteries, vented lead acid, these are the batteries that we see that are filled with electrolyte. They have a lot of electrolyte in them. And as they discharge, they release hydrogen gas. This is a small amount, but they should always be kept in a vented room because of this. As the gas gets vented, that gas comes out of the water and the electrolyte. So therefore, we see electrolyte levels go down, and this is why we periodically have to add distilled water to these type of batteries. Now, some of the advantages of these batteries is they can be quite large, and they have a very long lifespan. You can get 20 to 25 years out of a vented lead acid battery. Now, another type of lead-acid battery is the VRLA battery, valve-regulated lead-acid. These are often referred to as sealed batteries or maintenance-free batteries, which is sort of a misnomer because they technically require more maintenance. Now, with these batteries, they don't release hydrogen gas normally. What they do is they have a reaction that recombines the gas, the oxygen, back into the electrolyte. However, if they overheat, you can end up with higher internal pressure in there that will cause a venting of hydrogen. And this is what the valve is for. If the pressure gets too high, you will vent hydrogen gas. Now, with these type of batteries, you cannot add water to them. So if they get in a situation where they get too hot and they vent hydrogen, that electrolyte level is permanently low. Okay, you cannot add water back to it. In a VRLA battery, they use oxygen recombination. The oxygen released from the positive plate travels to the negative plate where it combines with steals electrons off there, and it will recombine to form hydrogen. This is the recombination effect of a VRLA battery. And this is why you don't have to add distilled water to it. However, keep in mind, no chemical reaction is 100% efficient. So over time, it does slowly lose electrolyte. And the failure mode of a VRLA battery is called dry out, which we're going to cover in the failure modes. Now, battery applications. Not all batteries are created equally. Different applications require different designed batteries. The batteries have different types of plates. They have different types of chemistries. All these things come into play when you want to choose the right battery for your application. If you don't choose the right battery, you may not get the lifespan you expect to get. First thing you have to look at with lead-acid batteries is their plates. The more plate surface area you have, the more capacity you have. This is why when you get larger batteries that have a lot more plate surface area to them, you have more capacity and you can get more current out of them. Now, also like in cyclic batteries, typically the plates will be thicker. Why would they be thicker? Well, when you're discharging and charging the batteries, you're creating heat. So the thicker plates allow they better deal with the heat generated by the repeating charging and discharging. So in cyclic batteries, we would expect the plates to be thicker to handle this, the heating effects better. We also have different chemistries. You can have lead antimony batteries. You can also have lead calcium batteries. These are the two most common batteries we see here in the United States. And the lead antimony battery, the advantage of this is the antimony is stronger. It helps dealing with heat better. It can handle the repeated charges and discharges. Originally, the batteries were all lead. And the problem with that is lead is a soft metal. And you couldn't build them very high, and they didn't handle heat very well. So by doping them with antimony, we were able to actually create much larger batteries, larger capacity that could deal with the heat better. Now the problem with antimony though is although it's good for cyclic applications, it's not ideal for stationary applications. This is because when it's left on prolonged charge, the antimony will begin to slowly dissolve into the electrolyte. This is referred to as antimony poisoning. And we'll see this as an increase in float current because you're getting contaminants into that electrolyte, drawing more current. We also have lead calcium batteries. Now lead calcium batteries deal with float applications, standby applications much better because they don't suffer from antimony poisoning. However, lead calcium batteries are not as strong as lead antimony batteries. They don't deal with the heat quite as well. So they're not ideal for cyclic applications. So we want to really think about the battery we're going to use for our application. Cyclic batteries, for example, we may want to go with lead antimony designs with thicker plates to better handle the heating effects of charging and recharging. Now you also have what's called SLI batteries, starting, lighting, ignition batteries. These are probably the ones we're most familiar with. They're used in cars to start the car. And these can be a lead antimony design or a lead calcium. The difference in these batteries, though, is these batteries have a tremendous amount of very thin plates in them, and they maximize the surface area. Why are we maximizing the surface area in these batteries? Well, by creating all that volume for the surface area, we can deliver a very high charge very quickly, a lot of current very quickly, which is required for a starting battery. So you're pulling a lot of current in a brief moment to start the car, and then what's the very first thing the car does? The alternator kicks in and recharges the battery. This is because these type of batteries are not designed for any sort of deep discharge. Any of you that know that have a battery that died, as soon as you recharged it, it never lasts again. In fact, it's dangerous to leave it like that because these can form dendrites, which I'll cover in failure modes, but actually can lead to fires. So again, we want to pick the right battery for the application. This is why I never use a car battery for a stationary application. They're not designed for it. Stationary batteries. Now these are the type of batteries, again, we're going to see in substations, telecoms, data centers, and typically we want a low antimony or a lead calcium design for these. The lead calcium, why? We don't get antimony poisoning in it. And the plate thickness is going to be dictated by the capacity we want. The more surface area, the more capacity you get. All right. Now, what I'm going to do is go into the failure modes of the batteries. Positive grid corrosion. This is the normal failure mode in a flooded lead acid or vented lead acid battery. In this failure mode, the lead alloy turns into a lead oxide. Now, if we think about it, what we're losing active material when this happens. Okay, because the lead alloy, again, is turning into a lead oxide. And the way I like to visualize this is if you think of two plates of metal that are touching, they have very low impedance. As you start pulling them away, what happens to the impedance? It will slowly go up. Okay. The same thing basically happens in batteries. As the lead alloy turns into a lead oxide, you're losing active surface area. So the internal impedance of the battery is going to go up. In addition, the lead oxide crystals are larger, so the plates grow. If you look at the bottom of this image here, you'll see there's a gap between the bottom of the plates and the bottom of the battery. This is to allow for plate growth. Now, I don't know how many people have ever gone into a battery room and seen the batteries bulging. Now, for VLA batteries, this typically is an indication that the plates have grown so much that there's no more room for them to grow, and these type of batteries should be replaced immediately as soon as you see any deformation, because it's a safety hazard. Because the next step is they're going to pop their top and they are filled with acid. So this is a dangerous scenario. You want to replace them immediately. But here's a question. Now, we know this is the common design failure mode for VLA batteries, but what can accelerate this? We can accelerate this due to heat. Heat is basically the enemy of the battery. What does heat do? It makes molecules move faster, which increases the rate of chemical reactions. So the hotter it gets, the less lifespan we're going to get out of a battery. What causes excessive heat? One, overcharging will cause excessive heat. Excessive cycling, excessive temperature. And as you get that, the chemical reactions will proceed faster, grids will corrode faster, and the internal impedance of the battery will rise. Shedding. This failure mode only affects VLA batteries. It's the slowing off of active material from the plates. The lead alloy turns into a white lead sulfate, and it drops. This is a normal characteristic of the battery. However, a small amount is very normal. So if I look at a vented lead acid battery that's been in the field, say 5 years, I should see just a very basic dusting there. If I see something like this image here, that's a flag. That tells me there is something wrong, okay? As the material comes off, again, this is going to be accelerated by heating. As that material falls to the bottom, I'm losing active surface area. The impedance of the battery is going up. Now, if enough of this sheds off to where it goes up and actually touches the plate, it can cause the plates to short, and suddenly what you'll see is the impedance will drop along with the voltage as well. Okay, the key thing to keep in mind here is that typically we're going to only see a little bit of this, and it should only be on flooded, it only concerns flooded batteries, VLA batteries. Now the next one, plate sulfating. This concerns both VLA and VRLA batteries. This is a normal condition that occurs in these batteries as they discharge. As the batteries discharge, the active plate material turns into a lead sulfate. Okay, and the lead sulfate, basically as that happens, you're losing active material. As you lose active material, what happens? The impedance goes up. Okay, it occurs both in flooded and VRLA batteries. And when we recharge the battery, we reverse this process. So the impedance will drop as the battery charges up. Now, what can cause a problem here? Well, if we undercharge the battery, then the plates remain partially sulfated. And the problem with this is that sulfate crystals get denser over time. They get harder. Now, we can force them to break down by using a equalization charge. This is where we're going to increase the voltage across the battery, the float voltage, for a period of time, and this is going to be done to try to break down sulfation crystals, and we can get capacity back in the battery this way. However, it only works for breaking down sulfate crystals. And now there's 3 phases of sulfation, phase 1, 2, and 3. They refer to the density of the sulfate crystals. Phase 1 and 2, you can reverse them by doing equalization charging. Phase 3, though, they're so dense, no amount of equalization is going to correct them. In those particular situations, you'd have to do a chemical treatment and then equalization, and typically at that point, you're just going to replace the battery, let's be honest. Okay. Okay. Short circuits in batteries. We can have both hard shorts and soft shorts. Now, a hard short is typically caused by paste lumps in the manufacturing process, and this is usually a manufacturing issue. This will show up fairly quickly after you put the battery in. If you put the battery in and you see a drop in voltage and impedance, basically what that's telling you is you had a paste lump in there that broke through the separator and shorted out to the adjacent plate. Now, soft shorts, on the other hand, these are caused by deep discharges. When we discharge a battery, they're only designed, lead-acid batteries are only designed to be discharged down to about the 80th percentile of their voltage, and SLI batteries less than that. Okay. When they get discharged, if you pass that 80 percentile, it's called watering the battery. The specific gravity of the electrolyte approaches out of water. And what ends up happening is the lead will begin to dissolve into the electrolyte. In VRLA batteries, these can get trapped in the separators. And now when you go to recharge the battery, okay, some of it may go back onto the plates, but it won't go back in the same place on VLA batteries, and in VRLA batteries it gets trapped in the separators, and it creates what we call dendrites. The dendrites can short the plates out, and we'll see this as a drop in voltage and a drop in impedance. Now, car batteries, like I said before, when they get over discharged, these are batteries that have a tremendous amount of surface area, a lot of plates and very thin separators in them. They're very thin in them because they're trying to maximize that surface area. So when the voltage goes too low in them, the lead gets trapped in that separator and will short those plates out. So when you go to recharge it, you still have those shorts in there. You have a whole bunch of micro shorts in the battery. And we hear all the time in the news about lithium-ion batteries catching fires. But in all honesty, the batteries that catch on fire the most are SLI batteries, car batteries, because of this scenario. Dry out, or loss of compression. These affect only VRLA batteries, valve-regulated lead-acid batteries. Now, unlike vented lead-acid batteries that are filled with electrolyte, VRLA batteries work in what's called an electrolyte-starved mode. It means they have very little electrolyte actually in them, and as we discussed before, we have a recombination effect that takes place on the negative plate to reconstitute the electrolyte. Now, this is not a 100% efficient reaction. No chemical reaction is, so over time it does slowly dry out. Now, what can accelerate that? Heat. Just like in a VLA battery, heat is your enemy, especially even more so with VRLA. Because in a VLA battery, a vented lead acid, you can always add electrolyte. In a VRLA, you cannot. So they are temperature-sensitive batteries and should always be kept in temperature-compensated rooms. Okay, you want temperature control when you're dealing with a VRLA battery, that is. And if they get too hot, you can lose gas through them. Lose hydrogen can get vented through the valve. And what can end up happening is this next failure mode, thermal runaway. This only affects VRLA batteries. In this mode, what happens is that we're venting hydrogen through the valve in the VRLA battery. And as this happens, you're losing electrolyte. So the battery is now going to draw more current, and it's going to run hotter. As it does this, it's going to vent more electrolyte. And as it vents more electrolyte, it's going to run even hotter. Now this can actually become a self-sustaining reaction. If this becomes a self-sustaining reaction, then you're going to get what's known as a thermal runaway. And the problem with the thermal runaway is it's only going to end in one of three ways. It's going to end in either a meltdown, a fire, or an explosion. So we want to always be careful with this. Now keep in mind, a thermal runaway is not going to happen overnight. In fact, I've heard a lot of people really call it a thermal walkaway because it is slow, and as long as we're monitoring our float current, we should be able to see it. And we'll get into that when we get to testing. But what can cause thermal runaway? Heat. Very simply, heat. And that can be to overcharging, to high ambient float voltages, low airflow, and one of the key things here is to be sure to use a temperature-compensated charger on VRLA batteries. And the last thing we're going to cover is loose connections. This is something that gets overlooked so much when testing batteries. People look at testing the batteries, but don't think about the intercell connections, the straps on them. This is critical because now think about the string, which you have. You have all these cells connected by these straps. And if you think about it in your head, you can picture these as like little impedances, little resistors of that. And now, as the current goes through, the charge current, the flow current goes through, you're getting small little voltage drops across there. What happens when you have a poor connection, corroded connection, loose connection, whatever it may be? You're going to get a larger voltage drop across it. So you're going to get high heat, higher heat. And this can cause problems. Not only can you get higher heating, but now you're getting voltage drops across the string. So what happens to that float voltage down toward the end of the string? It's getting lower and lower. If it gets so low that you're undercharging the battery, what are you doing? You're leaving that battery partially sulfated. The longer it stays in that condition, the harder it is to reverse it. So intercell connections, loose connections, are a priority. They have to always be tested. Extremely important. So how do we do the maintenance on batteries? Okay. Well, the issue with that is that there's no single test in the world that's going to tell you the whole story with the battery. We want to determine where the condition's at and where it's heading and how fast. So we want to gather as much data as we can on these within reason. These are the different types of tests you can run. You can do a visual inspection, float voltage, float current, ripple current, specific gravity, temperature, discharge testing, ohmic testing, and strap resistance. A visual inspection. This is probably the simplest thing to do, and it's critical. We want to check the entire system. On flooded batteries, you're going to check that electrolyte level. You'll see there are 2 lines on it, on the top of the battery, and that electrolyte should be in between those 2. We want to make sure our ventilation systems are working and everything's clean, and the battery support system, the rack and everything is solid. Check the battery for cracks, leaks, or deformations. Critical. If you see this, any of it, replace that battery. No questions asked, just replace it. Leaks can lead to ground faults and are dangerous. Deformations are basically saying that battery is about to burst. Strap corrosion. We want to clean that immediately. Strap corrosion, what's it going to do? It's going to lead to poor connections. Those poor connections will increase the heating and cause voltage drops. Okay, and always record the information as well. Float voltages. We're going to measure across each cell and see what the float voltage is and measure it at the post. This has to be done while it is in a float mode. And I've had people ask me, what's the proper voltage? Well, basically, when you get a battery, always, when every battery string you have, get the data sheet for the batteries. Those data sheets are going to tell you what the proper float voltage is, both the minimum and the maximum. And some of them will also have temperature compensation in them. So they'll have you check the temperature in the room and make sure they're in between the right voltages. This is critical. If you have it too high, you're going to accelerate corrosion. And you could accelerate dryout. If you have it too low, you're going to have plates that remain partially sulfated. And that's what this slide was all about. Next slide, float current. Okay. When the battery is in float mode, it's going to be drawing a low current. Okay. It's also critical to measure this. Now, you can measure it anywhere in the string, on a series string, because of Kirchhoff's law. The current will be the same throughout the string. So wherever you want to put the current clamp, you're fine. Okay, but it's going to be a DC measurement. You can measure the DC float current. Now, when measuring this float current, let's think about what we already talked about. Okay, if we have a lead antimony battery and that's sitting on float that has a high antimony content, we may see that float current increasing over time. This is an indication that we have an antimony poisoning occurring. Now, if we have a VRLA lead calcium battery, and we see float, now lead calcium batteries will draw less float current, but if they start to dry out, we're going to start seeing that float current going up. And if we see that float current going up over time, that's a flag. That says there is a problem, and we want to address that. We want to make sure that the float current doesn't go up to a point where it's going to end up leading to a thermal runaway. So we want to check things like the temperature. We want to make sure that we're using the right type of charger, temperature compensated charger on VRLA batteries. And we want to make sure there's no ground faults in that circuit. Right? And that's what that slide is. I'm horrible for that. I'll start talking and go right through a couple slides, but all the information is here. Ripple current. Okay, when we deal with a battery, they have to be charged. So we have a charger that's converting AC to DC. That reaction is not 100% efficient. You're always going to have some type of ripple current on there. And the AC current, batteries don't want AC going through them. Okay, this will generate heat. Now, IEEE will tell you that you should have no more than 5 amps for every 100 amp hours of ripple current going through, or AC current going through a battery. Now, if you're dealing in a substation environment, typically this is not going to really be much of an issue because you have very large batteries that sort of do act like filters. So it would take quite a bit of substantial amount of current, and the only real current source is the charger. Okay, so if you do see high ripple values in a substation type environment, typically that's a sign that you have a charger problem. Now, not the same is true in telecoms necessarily. In telecoms and data centers, you can have the ripple coming from the load as well. So we want to always look at that too, and especially in UPS environments. In those environments, you can run into issues because of not only the magnitude of the ripple, but the frequency of the ripple. Low frequency ripple can have much more dramatic effects on a battery because it stays at its peak and valley for a longer duration of time at a lower frequency. It has a longer period. And the problem that you can run into is if I have a minimum and a maximum float voltage that I'm supposed to be at. If I have a low frequency ripple that's going through my string, that's raising up, going above the float voltage, then below the float voltage at 60 times a cycle, what I'm doing is rapidly charging and discharging the battery. Okay, this will lower its lifespan, and this I have seen on some types of UPS systems where you can see this low frequency on there. Okay, specific gravity. This is where we're going to use a hydrometer and measure the specific gravity of the electrolyte. This is only obviously done on vented lead-acid batteries because you have to be able to get to the electrolyte. On a sealed battery, a VRLA battery, you cannot do this test. And what this test will actually give you is the state of charge of the battery, but not the state of its capacity. It's just going to let you know if the battery is fully charged up. So we can actually get the same data by examining the float current as well. This is very important. Your temperature, okay, is that temperature, again, the higher the temperature, the less lifespan you're going to get, okay? It accelerates corrosion in the vented lead acids, and it accelerates dry out in valve-regulated lead-acid batteries. Just a rise of 10 degrees Celsius will half the life of a battery. This is why it's critical with VRLA batteries, keep them in temperature-controlled rooms. You do have a little bit more leeway with the VRLA battery because, again, you can add electrolyte to it. Discharge testing. All right. In discharge testing, when we do a discharge test, this is the only one that's going to actually tell you the capacity you have left in the battery. There are several types of discharge testing: acceptance testing, performance testing, service testing, and again, it's going to tell you how much capacity you have. Now, this test does take time. You need to go through first, make sure that you have your straps are good, they're all torqued properly. You typically would run an equalization charge before you do this, and this is typically an offline test, which means that if you're in a critical application, you got to bring in another set of batteries. Otherwise, you could end up going offline if you had a failure during the discharge test. After the discharge test is done, the batteries need to be recharged and re-equalized. Okay, so this is a long test. Typically, this is done at commissioning of a string, and then you would take the lifespan of the battery, divide it by 4, and that's how often you would do a discharge test, basically 4 times in the lifespan of the string. The issue is, though, batteries can fail in a shorter period of time than that. So there's also ohmic testing. This provides a state of health rather than a state of charge or state of capacity. As the battery ages, you have corrosion of the plates, plate sulfation, and as this happens, the impedance will increase in the battery. There are 3 types of ohmic testing: resistance, conductance, and impedance testing. And 2 of them are AC, impedance and conductance. Resistance is DC. The problem with DC is that it's only checking the resistive characteristics of the battery. A battery is not a resistor. This here is a schematic of a battery. And what you can see is there are several resistive elements on there representing the electrolyte and the plates, but there's also that big capacitor on the top labeled DL. That's called a double layer effect. And basically what a double layer effect is, whenever you have a liquid that touches a solid, that creates a capacitor. And when a battery discharges or ages, the first thing that's going to change is that double layer effect. And since batteries aren't resistors, when you look at it doing an AC test, you will see the changes quicker. And now I said before, AC is not good to put through a battery, but we're talking about a small amount of AC and a small amount of time. So doing it for testing is not an issue. Okay? It's when AC is left on the battery for prolonged periods of time that you can get those heating effects. Important about ohmic testing, it is not an absolute test. No ohmic testing in the world is going to tell you that your battery is good or bad. It's a relative test. It means that we're taking the measurement that we get today and comparing it to the previous measurement to see how much the battery has changed. If it's changed by a certain amount, then that's a flag saying we have a problem, we need to investigate. Also important, different instruments will give you different values. This is because different instruments operate at different frequencies. And you can see from the formula on the right here, as my frequency goes up, my capacitor reactance goes down. As my capacitor reactance goes down, so does my impedance. So if I have 3 different instruments all operating at different frequencies, they're going to give me 3 different ohmic values. Which one's correct? They all are. Because it's not an absolute test. It's a relative test. We're comparing the reading we get today to the previous one. That's why the key is not accuracy. The key is repeatability. You have to be able to get the same measurement time and time and time again. That's the key in doing ohmic testing on a battery. Intercell resistance. Okay. Again, we want to check the straps. It's critical. Many times I've seen where I have a battery with a high impedance only to find out that the straps are, there's several straps with very high impedance that need to be corrected, and the string needs to be equalized, and everything comes back to normal. So how do we do the intercell resistance? Okay. Now, we can do it with many battery testers. I actually also do intercell resistance. I'll put an AC current through it, and they'll measure the voltage drop across it and calculate the impedance of it. You can also do it with a DLRO, a low resistance ohm meter. But now there's a problem. If you're going to do it with a DLRO, you have to keep in mind that you have float current going through it. A low resistance ohm meter does the test using DC when you're measuring a strap. So it's only pushing current in one direction. So if I have float current already going through the battery, I'm going to get a different reading in one direction versus the other. So how would I take the reading? What I would need to do is take the reading in both directions and take the average of it. Some low resistance ohm meters do have that function on there. Okay. But again, if you're going to use DC, you have to do it in both directions. Also important, what I've heard is people tell me, I want to do DC because use a low resistance ohm meter so I get an absolute measurement. You're not going to get an absolute measurement on a battery strap. It's always going to be relative. This is because in order to get an absolute measurement when you're doing a low resistance ohm meter test, you have to have a certain gap between the lead that's injecting the current and the lead that's picking up the voltage. Because you have to compensate for the current density of the material that you are testing. So on a battery strap, to do that, you have to look at the cross-sectional area of that battery and basically multiply that by 3. And the thing is, a battery strap doesn't have enough overhang for you to separate them that much. So you're going to be basically doing the measurements right from the terminals, and it's going to be a relative measurement. IEEE 450 will tell you that if a battery strap deviates by 20%, it needs to be addressed. So again, it's a relative measurement. Once you see that change to 20%, address the battery strap and clean it up. Okay, it's going to be a connection issue, and you clean the terminals and torque everything up. Okay, VRLA batteries. What type of testing are we going to do? Well, their failure modes are dry out, thermal runaway, they sulfate, and you can get soft shorts if you deep discharge them. So what tests are we going to do? We're going to do inspections, float current, ripple current, ohmic test, and intercell strap measurements. These are the tests we want to run. How often on a VRLA? You want to do it quarterly on them, okay? Because this is how often you can have issues with them. They can fail within that amount of time, okay? Now, important when you're running an ohmic test, how do you do it? There are many things. Now, when I say ohmic, I'm talking about any type of ohmic test. You must follow this procedure. Is that there's many things that will affect an ohmic reading. The type of battery, its charge, temperature, make and model of instrument being used, which we just talked about. The probe type that you're using, string length and configuration, all these things have an impact. So there's 4 rules you must follow. 1, the battery string must be fully charged. If it's not fully charged, it's partially sulfated, which means, again, you're looking for a relative measurement. You're comparing this measurement to your previous one. So you have to always have the battery in the same state. If it's not in the same state, you have no comparison. Okay? You want to use the same make and model instrument. If you do not, you have to establish a new baseline, which I'm going to get into in a minute. The same probe type needs to be used from one test to another. If I use extension probes or Kelvin leads one time, if someone else goes and uses a pistol gun the next time, I'm going to get different measurements. So you always want to use the same type of probes. And the other thing is you want to take the measurements from the same point on the battery. Recommended to always take the measurements from the posts. If I take it from the post one time and someone else takes it off the hardware, they're going to get different readings. So again, we want to keep it apples to apples whenever you do an ohmic test. And how do we establish a baseline? This is a baseline, sometimes I've heard people say this is like a magic number almost that you have to get from the battery manufacturer. No, it isn't. A baseline is a reference value. It's saying this is where I'm starting from, and this is my reference for as the batteries age. Okay, and IEEE would tell you you don't want to get the baseline from battery manufacturer because you don't know what instrument they used. The battery's not in your string. The battery most likely is a green battery and hasn't gone through formation. Okay, so and you also don't want to get the value from a test instrument manufacturer because you don't know the condition of those batteries where they use for the testing. Okay, IEEE basically tells you you want to establish your own baseline value. Okay, so basically a baseline is not a magic number. It's basically the value of the string when you first test it. You want to make sure you have a good string when you establish baseline, and it's going to be the average of that string. And there are softwares that will calculate the actual baseline value for you so you don't have to do that. How do we analyze the data? Well, there's 3 different ways that you can analyze data. One is by comparing cell averages. So I'm going to test every cell in the string. Then what we do is we're going to make an average them all together and come up with an average value. Then we're going to look at each cell compared to that average to see how much it deviated. If it's deviated by 30 or 50%, that's a flag. That says we need to look at this cell and see if there's an issue with it. Okay. Now, let me give you a possibility here. What happens if all of the cells are within 5% of each other, but the whole string is aged? You won't see that through cell average. That's why we look at baseline too, from the first time you did the test to now. This will tell you how much you're going to compare each cell to that baseline value. That'll tell you how much the whole string is aged. And if we see multiple cells deviating from baseline by 50%, that's a flag that says now it's time to do a discharge test or some type of test to make sure that we still have the capacity we expect to have in the string. The last type of testing you can do, you need software to do it. It's tracking the changes of the impedance test. And what we're going to do is you're going to look at the impedance value of each individual cell every time it was tested throughout its life and see how much it's changing. What's this going to tell us? Well, when you buy a battery, it comes with an expected lifespan. VRLAs, typically 5 to 8 years. VLA batteries, 20 to 25 years. Well, if you're not even through half its lifespan, you see that impedance on these cells going up. That's a flag. That says you have a problem. You may have the wrong type of battery for your application. You might have environmental or maintenance issues, or they just could be poor quality batteries. But that's a flag, and it also lets us know when we need to put money aside for a new string. Maintaining VLA batteries. Their failure modes are positive grid corrosion, shedding, sulfating, and again, you can get soft shorts from deep discharge. We want to do basically the same things. We're doing inspection, flow current, ripple current, ohmic testing, intercell measurements, and with these they also do discharge testing as well. How often? Typically, ohmic testing is on a biannual basis, every 6 months with these. Now, there is a caveat to testing these. When you're doing ohmic testing, is these batteries can be quite large. That means they have a lot of surface area. The more surface area they have, the lower their impedance, which means if you're using an ohmic tester that's using a small amount of current, you won't get a very large voltage drop across it. So you're going to be in the mud trying to do the measurement. Okay? So typically, if you're going to be doing VLA batteries in a substation environment or any environment where you have these large batteries, if you're going to do ohmic testing, you're going to need something that can put out enough current to get a large enough voltage drop to be able to see your results. Otherwise, what will end up happening is you're going to use this small little handheld meter, and what's going to happen is everything's going to read the same regardless because it just doesn't have the resolution to see these large batteries. And the last topic is parallel strings. A VLA battery, a vented lead acid or flooded cell, fails in what we call a shorted mode. That means that when it fails, you still typically can get current through it. So in a series string, even if you have a battery that failed, you can get current through. A VRLA battery, because it fails by dry out, fails in what we call an open mode, because as it dries out, the separators shrink and pull away from the plates. So if you have a series string with VRLA batteries and you have a failed battery, it'll fail open. You may not be able to get current through that string. This is why with VRLA batteries, if you're doing a critical application, you should have a parallel string, okay, with VRLA, because if you get an open battery in one string, you still can get current through the other. Now, when we test a series string, we're injecting current through one battery, and there's only one path for it to go. So all the current will go through that battery. When I test a parallel string, I'm introducing another path. So when I inject the current to test it, the current can go through the parallel path as well. What's the problem with that? Well, it can be a problem in locating a poor cell. If I have a cell that has gone bad, what can happen is that it will change the impedance on both. It'll change the current flow through both strings of the battery. So typically, what's recommended is to segment parallel strings, but there is another alternative. Some battery testers have the ability to measure escape current in parallel strings. So instead of segmenting them, you can use an extra CT and put it around the parallel string so that it can measure what's called the escape current going through the parallel string. So you always will get the proper measurement on each battery. So even if you had a battery that failed or a battery that's impedance is rising, you will find that battery and not end up seeing all of them change because of that. Alrighty, and questions or comments? I know I rocketed through that. I had a lot of material to cover in a very short amount of time, so hopefully it wasn't too quick. Alrighty, so Mike, I'll turn it over to you if there's any questions.
All right, thanks, Andy. So that concludes our presentation portion of the webinar, and we're going to move on to a Q&A session. Just as a reminder, if you'd like to ask a question, send it through the question box on the webinar controls on the right side of your screen. And our first question is, when do you use parallel strings? So you want to touch on that, Andy?
Yeah, parallel strings are basically when you have a critical application, and if you're using VRLA batteries, vented valve regulated lead acid batteries, because they can fail in an open mode, if you use a series string with them and you get a failure, you may not be able to get current through. So when they're needed, they may not be there. This is why you want to use them in a parallel mode, because if one fails, you can still get current through the parallel string. So whenever you have a critical application and are using VRLA batteries, you want to use parallel strings. Otherwise, you can use vented lead acid, VLA batteries, and use a series string with them. Those are flooded batteries, obviously.
All right, thank you for that. Okay, here's a question just came in. How is ripple current calculated?
Basically, what we're actually doing is we're taking a measurement using a CT right on the string. If you have a charger, like I said, a charger has a rectifier in it. So it's going to be converting AC to DC. But no rectification is 100% efficient, so you will have a certain amount of ripple current on there. And all it's going to be is an AC current. So you're going to put a meter on there, basically a current clamp, that will measure RMS current. Typically, it'll be a low value. If you see a high value on there, that's a sign that you have a charger problem, or in some applications like UPSs or telecoms, you may have load issues.
Okay, thank you. The next question, what are your measurement points for ripple voltage?
It's not voltage, it's ripple current we're looking at. So we're not actually measuring a voltage, we're actually measuring the current going through. So if you're using a clamp, you can put it anywhere in the string, okay, and anywhere in the series string. If you want to calculate the ripple current, what you can also do is use the strap as a shunt. After calculating the ohmic value of a strap, you can use that as a shunt to actually measure the AC voltage drop across it, and then you could see the actual current, calculate the current by dividing the resistance of the strap into the voltage and coming up with the current.
Okay. Next question is, can you talk about lead antimony selenium design?
Oh, okay. What the selenium battery is, now that's actually more common in Europe. When it was discovered that they had this lead antimony issue with these high antimony batteries, and you could get antimony poisoning, the question was how to resolve it. So here in the United States, we pretty much went to lead calcium batteries. In other areas, they've gone to lead selenium. And basically what the lead selenium battery is it is basically a lead antimony battery, but it has a very low antimony content. So it's not really subject to the antimony poisoning that you get. All right. The main reason it didn't catch on here is that it's a little bit more expensive than the lead calcium. The lead calcium is typically a cheaper battery, or a lower cost, I should say.
Okay. All right, next question. When 1.5 volt rechargeable batteries are connected in series to establish a 6 volt DC battery, the connections direct to the batteries are spot welded. We would like to replace the batteries and solder the wire connections. Are there any issues with doing that?
Oh, soldering on a battery, that can cause heating issues in there. That's why typically when you do anything with a battery, you're going to do spot welding on it. Now, do you know if they're making it in a battery pack or what they're doing here?
Doesn't tell me.
Okay. What I would suggest is for this particular question, I would ask them to probably contact us, okay, and let's discuss that, what their application is. Because typically you do not want to solder to a battery.
Okay. Now, next question, is there a load requirement or a code requirement to prevent battery thermal runaway?
A code requirement. It's funny, when you deal with batteries, many times the answer is it depends. And with this, there's no code requirement. What we're actually looking at here is monitoring that float current and seeing how high it's going up. If it goes up, the data sheet of the battery is going to dictate the nominal float current. So if we see it really going up, what I would recommend is getting that value from the battery manufacturer to see about what the actual alarm would be for that, because that can change from battery to battery depending on the chemistry and the plates and everything in it.
Okay. Next question. How much current using DLRO should be used for strap measurement?
Interesting question. Many times when they use a DLRO, they're typically just using 10 amps to do it. Now, this measurement you're going to be getting is in the microohms, obviously. Now, again, regardless of how much current you're going to use, you're still going to have a relative measurement. So what you're looking for is a change of 20%, and that's per IEEE 450. Okay, so when I look at that strap measurement, if it's changed by 20%, that's a flag. So regardless if I'm using 10 amps, 100 amps, whatever it may be, that's what I'm looking for, because again, I'm not getting an absolute measurement on this. It's always relative because I don't have enough overhang on that to be able to compensate for current densities during a low resistance ohm meter measurement. So therefore, we're going to do it right off the posts and compare that measurement and see how much it's changed. That's the name of the game with that. 20% is the number with that.
Very good. After an equalization charge, is there value to adjusting the specific gravity with additional acid?
Well, the function of an equalization charge is basically twofold. It's to break down sulfation crystals, and it is also meant to balance the battery string. So what is happening when we look at the specific gravity, we're looking at the state of charge of the battery. So balancing them would be a fairly good thing to do. So if we do want, you can actually do that, because what it's going to do is help balance the charge on the batteries, and you will get a better balance. Because remember, in a battery string, a battery can act as a source or a load. If you have one battery that's lower than the rest, it's going to be a load on them and drag them down. So yes, after you do that equalization charge, by adding electrolyte to get the specific gravities the same, what you're basically doing is further balancing them.
Next question is, for ripple, can I measure my AC at the output of the charger?
You want to, well, it's going to basically, remember, Kirchhoff's law is that it's going to be a constant throughout the entire circuit. So you can measure it at that point, provided you're not, yes, actually you can. I'm just sitting there thinking about it. You should be able to see it at the output of the charger, because it is just going to be going through the string, so the current should be constant.
Okay. When testing for ripple current, is there a ratio that's acceptable, AC versus DC current?
It's not so much AC versus DC, it's the AC versus the capacity of the 8-hour rated capacity of the battery. So if you have a battery that has a 100 amp hour 8-hour rating, your ripple shouldn't exceed 5 amps. So it's basically, that's the actual recommendation, is not to exceed 5 amps for every 100 amp hours of the 8-hour rated capacity.
Thank you. On VRLA batteries, when we see staining from acid, is it time to replace the batteries?
When we see staining from acid?
Yeah.
I'm assuming that's probably on the post, so that actually would be an indication of a leaking post. So yes, if you see acid, I would actually replace that right away, because that acid can actually lead to ground faults.
Okay. Now, how is battery capacity defined? What is meant when you say a battery has failed to reach 80% capacity on a discharge test?
Oh, what they're looking at there is the battery is defined by its 8-hour rated capacity on its data sheet. So if it's rated for a certain amount of capacity, that it should reach over an 8-hour period. Now, the capacity of a battery is not something that is hard-coded. If I say I have 100 amp hour capacity, it has to be at a certain discharge rate, because the faster you discharge a battery, the more load you put on it, the less capacity you're going to get out of it. Okay, so that we're going to be looking at its data sheet. You look at the 8-hour rated capacity, and that is with the given load that's on there that would make it reach 80% of its voltage. Okay, would be its rated capacity. So when they talk about the 80% when you're doing a discharge test, what they're really talking about is not exceeding 80% of the rated voltage of that battery. Okay, so if you drop below that, it's about 1.75 volts per cell. If you drop below that, if you're doing a discharge test and you see a cell drop below that, if it's just one cell, you would typically stop the test, jump that cell out and continue. If it's multiple cells, you would stop, period. Okay? But that's typically what they're talking about when they're talking about 80% of the capacity, is don't pass that 80 percentile of the battery voltage, because if you do, you will be deep discharging the battery and can accelerate dendrite formation, which can lead to soft shorts in the battery.
Okay. Next question is, how often should we recharge rechargeable batteries when not in use in order to ensure a state of readiness?
That's a very good question, because I've seen people not do that quite often. And again, I would always refer to the battery manufacturer for that, but I would never let a battery sit on a shelf for more than 3 months without topping it off and charging it up.
Okay.
And by the way, that would go for any chemistry, including lithium ion. The only one that does not necessarily apply to that is NiCad, because it's the only one that can charge down all the way down and be brought back up, but that may require conditioning of those type of batteries, though.
All right, now here's one. What are you seeing for arc flash issues on DC systems? How do we calculate DC arc flash incident energies for normal battery maintenance? And what if there are no overcurrent protective elements outside of the battery string, such as fuses or a DC breaker? As in some systems.
I do not have an answer for that, but if you get their information, I can get you in contact with someone who does.
Perfect. Can you over-equalize or equalize too frequently?
Yes, absolutely. You can cause excessive heating. Whenever doing an equalization charge, always, always, always do it per the battery manufacturer's recommendations.
And then how long after a load bank test is completed should an equalized charge be started?
Well, you're going to have to recharge it. You're going to have to recharge the battery first and then probably run the equalization test. And again, whenever you're dealing with an equalization test, because you are going to be raising the voltage above the standard float voltage, you always go with battery manufacturer recommendations, because the last thing you want to do is void their warranty or damage the batteries.
Right. What effects does a solar charger have on a battery? Does it cut the life of the battery shorter?
Well, it's interesting when you're dealing with the solar, because you're going to be dealing with a cyclic battery in that case, not a stationary battery. If I'm assuming they're talking about solar backup batteries, because those batteries will charge and discharge repeatedly. So testing them is going to be a tricky proposition, because you never know if they're fully charged or not. And since they're not fully charged, they're partially sulfated. So the lifespan you get is going to be shorter. So I would definitely recommend a lead antimony battery in that case, because you will get more cycles out of it, and you are going to be doing a lot of charging and discharging in those solar applications. Okay, but the actual testing of it can be problematic, because you really need the battery fully charged in order to do the testing.
Okay, we've done our last couple of questions. Considering VLA batteries. Do older chargers using an auto transformer perform better, worse, or the same versus solid-state chargers?
I haven't seen that much of an issue with them either way, really. I mean, now keep in mind, a lot of my experience with VLA batteries is substation, so the ripple frequencies and the ripple content are relatively low. Now, when you get into UPSs, I have seen some issues in UPSs with low frequency ripple caused by some of the solid-state chargers, okay? But that is by far the minority that I've seen, and I believe those particular manufacturers are addressing that issue as well.
Okay.
But otherwise, I haven't seen too much of an issue.
Alrighty. Here's one asking what should be the DC current flowing through the battery when it's connected to a charger in float mode?
That is going to be on the data sheet of the battery. That's why it's critical to get that data sheet of the battery, because that is going to tell you what your float voltages and float current should be. And that's a critical spec. It's not something that is, I mean, you can ballpark it, but you shouldn't. You should always get the data sheet of the battery. And that information's right on there. Can't stress that enough.
Can we do equalization on any type of batteries?
Again, that is a battery manufacturer question. Be careful with equalization charge. Some manufacturers of VRLA batteries may tell you not to equalize them because you are going to be generating heat in them. Now remember, in a VLA battery, we can add electrolyte. In a VRLA battery, we cannot add electrolyte, so you have to be extremely cautious. If you're going to do an equalization charge for one of them, go to the battery manufacturer because they may tell you do not run an equalization test on these particular types of batteries.
Is there any difference in impedance value on the battery if it's tested on different points, either on the strap or on the bolt where the connection is?
Yes, because the battery is a low impedance device and the strap is a low impedance device, and it also depends very much on the material that the hardware is made of, because you can have something like a stainless steel hardware that can have actually a higher impedance than the actual battery does, depending on the size of the battery. So again, we want to make sure we're taking the measurements in the same location. The ideal location is to take it from the post. Now, I do know that in some applications with some of these batteries, it's very difficult to do that. Some of these batteries are mounted on their side. You can only get on the hardware. The only thing I can recommend there is if you have to do it on the hardware, you're going to look, because the hardware is going to be the majority of the impedance reading, especially if it's stainless steel. So you really got to look for smaller changes. So like I said, when I'm doing an impedance test, I'm looking for, with a VRLA battery, a change of 20 to 30%, with a VLA battery, 30 to 50%. But if I have to, it's not recommended, but if I have no absolute choice but to go off the hardware, I'm going to lower those values down substantially. Because again, the hardware, especially if it's stainless steel, could be the majority of your impedance reading.
Okay. What is meant by a capacity test showing over 100% capacity during a discharge test?
That can happen because the batteries are rated for, again, 8-hour rated capacity. So you can get, for a period of time, over 100% capacity out of a battery. It won't last, but you can for a period of time on new batteries. Now, keep in mind, when you first get a battery, typically those batteries are going to be what's called green batteries, okay? So when you first test them, they haven't completed their formation. Now, if you have a VLA battery, a vented lead acid battery, typically if you just leave them on charge several days, a week or so, they're going to be have full formation. And I guess I should explain what formation is. I really sort of skipped right over that, didn't I? Is that when a secondary battery is made, I said in the beginning that it's not charged. It requires a secondary operation to charge it. That's called performing a formation. When you buy a new battery, it's never fully formated. So, like I said, a VLA battery, vented lead acid, you're going to put it on charge. When you first do your first commissioning discharge test, you may find you don't get full capacity. With a VRLA battery, a sealed lead acid, it can take 3 months for it to reach full capacity. With a gel cell, it could take over a year to reach full capacity. Okay, so when you first do the test, you may get a lower capacity rating. As the battery completes its formation, you may get higher capacity than you expect out of it. Okay, but as it ages, don't fear, the capacity will come down.
Okay, last question. Do you recommend AGM type batteries for solar sites?
Oh boy, that's a very interesting question. The VRLA batteries for solar sites. Well, let's think about this now for a minute. With a VRLA battery, if you're going to use a VRLA, you have to have it in a temperature-controlled environment. You're going to want a temperature-compensated charger on it. Okay, and the chemistry, you need to take that into account. You're going to want to use a lead antimony. You want to use a cyclic battery for this. Okay, you don't want to use a calcium because in a solar application, you're charging and discharging repeatedly. Okay, so you're going to be heating the battery. Me personally, I would go with a VLA battery in a solar site because of the simple fact is I'm going to have, it's going to be less temperature sensitive, and I will get a longer lifespan out of it as well. Okay. Again, a VLA battery, you're good for 20 to 25 years on those. But the important thing is get the right chemistry battery. Get something that's made for cyclic applications, not stationary applications in the solar site. Because it's going to charge, and then it's going to discharge at night. It's going to charge, and it's going to discharge at night. So it's constant cycling.
Okay. One more just came in.
Okay.
Is it necessary to check specific gravity for NiCad batteries on a regular basis?
With NiCad batteries, again, that's going to sort of give you a state of charge, but they're a little bit a different animal because in a lead-acid battery, you're dealing with an acidic electrolyte. In a NiCad battery, you're dealing with an alkaline electrolyte. It never hurts to take a specific gravity, but keep in mind, the NiCad, because it has an alkaline electrolyte, material doesn't readily dissolve into it, so that when we look at a lead-acid battery discharging, as it's losing capacity, you see the voltage slowly going down, and as it gets older and older, the voltage keeps dropping. With a NiCad battery, because it has that alkaline electrolyte, that voltage will remain pretty rock solid through its discharge and its aging process, but then when it gets to end of life or end of charge, it's going to drop very rapidly. So it has a different profile to it as well. Okay, so as far as doing specific gravity testing for it, I would talk to the manufacturer and see if they really feel that there's a requirement for that particular type of NiCad battery. But with NiCad batteries, it's typically best to do a discharge test on them to maintain them.
Okay, one more just popped in. Why is charging AGM battery different from lead-acid batteries?
An AGM is a lead-acid battery. It's a glass mat. That's just talking about the separator. So there's no difference in charging them. It's just the only difference with a VRLA battery is you want to use a temperature-compensated charger. You really should use it for all of them, but it's really required for a VRLA battery because you want to make sure that you're not putting too much current through it, because if you accelerate the dry out, you can't add electrolyte to it.
Okay. Well, Andy, thank you very much. This is going to conclude our time for today, but we really appreciate Andy Sagl and the experts from Megger. If you have any further questions or would like to find out more about our Transcat's product and service offerings, please contact us at 1-800-800-5001. You can see us on the web at www.transcat.com, or you can email our Director of Marketing, Nicole, directly at nvanwert@transcat.com. We'll be sending out the slides and the audio recording of today's webinar within the next few days. So thank you all for joining us today. We hope you got something out of today's presentation. and that you continue to join us for future Transcat e-learning webinars. Thank you.
Thank you.